Precision Measurement for Machinists, a MasterTask multimedia program. Lesson 9, Open Setup Inspection. At times, workpieces must be measured using a variety of measuring instruments on a precision inspection table. The measuring instruments and workpiece holding devices must be selected, set up, and used correctly in order to obtain accurate measurements. This process is generally called Open Setup Inspection or simply Open Inspection. Open Setup Inspection is sometimes required for first piece inspection after machine setup. It may also be necessary for very short runs for a prototype or one-of-a-kind workpieces, or in other situations which do not justify the cost of making production gauges. In this lesson, you will learn the basics of Open Setup Inspection. In Part 1, you will learn about digital and dial indicators. In Part 2, you will learn about inspection tables and surface plates. You will also learn about the most common workpiece holding devices used in open inspection. Part 3 will show you how to properly select and assemble precision gauge blocks. And in Part 4, you will learn about mechanical and electronic height gauges. Part 1, Indicators. One of the most versatile measuring instruments used in open setup inspection is the indicator. Indicators are used not only for workpiece inspection, but also for machine setup and maintenance. This indicator is being used to check the runout on the spindle on a CNC lathe. A typical indicator consists of a dial where the measurement amount is shown, either a spindle or a lever, a contact point which contacts the surface being measured, and precision gears inside the housing. The face of every indicator is marked with the units of measurement. Typically, the dimension shown is the increment of each individual mark on the face. On this indicator, for example, each mark indicates a movement of 1/10,000th of an inch. An actual measurement is determined by multiplying the number of marks times the unit of measurement. Here, for example, the dial points to 10, 20, 30, the 37th mark. Since this indicator measures in tenths, the reading of 37 is multiplied by 1/10,000th. The result is 3 thousandths and 7 tenths. There are two basic types of indicators, dial indicators and test indicators. This is a typical test indicator. Test indicators have a hinged lever with a ball on the end which contacts the surface being measured. The test indicator measures the amount of movement of the tip. Measurements can be made in either direction that the lever rotates. The dial on most test indicators is called a balance dial. A balance dial is most appropriate for measuring relatively small variations in dimensions. Balance dials measure on either side of the zero. Test indicators are best suited for comparative measurements. In other words, rather than measuring absolute dimensions, they measure the amount of variation from a set standard or a known zero point. A test indicator would be used for such procedures as measuring the difference between the diameters at several points along a workpiece. This might be done to determine the straightness of the feature. Test indicators are also used to measure flat workpiece surfaces. Here, for example, is a measurement of a parallelism tolerance. Another common use of test indicators is to measure a round rotating workpiece. This would be done when measuring circularity, runout, or a position tolerance applied to two concentric diameters. In addition to measuring workpieces, test indicators are commonly used in machine setup. For example, here you see a test indicator being used to dial in or locate the center of the set point on a workpiece fixture. This is an example of a dial indicator. Rather than having a hinged lever, a dial indicator has a spindle which moves in and out. On the end of the spindle is the contact point, which contacts the surface being measured. Dial indicators are typically used to perform absolute measurements. An example would be measuring the height of a workpiece. On many dial indicators, the contact point can be replaced with an appropriate size and shape for a particular measurement. Changing the contact point is as simple as unthreading the existing contact point and threading in the replacement. Contact points are typically made of hardened steel, although they can be made of carbide. The ends can be flat or rounded. The proper shape of contact points must be used in order to provide the best points of contact between the indicator and the surface being measured. Flat contact points are used when measuring rounded or contoured surfaces. Rounded contact points are used when measuring flat surfaces. Most dial indicators have a continuous type dial. Continuous dials are more suited to measuring specific dimensions rather than measuring variations in dimensions. The numbering on a continuous dial goes in one direction from 0, usually clockwise. Some indicators provide a revolution counter, which counts the number of revolutions of the primary dial. As a measurement is taken, the primary dial and the revolution counter rotate simultaneously, counting upward from the preset 0 point. To determine the total measurement, the number of complete revolutions is multiplied by the range of the dial, for example, 100 thousandths on this indicator. Then the additional movement of the main dial is added. The result is the total indicator reading. This device is called a digital indicator. Digital indicators provide a numeric readout of the measurement. This particular digital indicator is part of a larger measuring instrument called a height gauge. You will learn more about height gauges later in this lesson. Before an indicator can be used, it must be clamped into an appropriate stand. Many types and sizes of indicator stands are available. An indicator mounted on a stand is sometimes called a test set. Frequently, indicator stands come with a magnetic base. An on-off lever allows the magnetic field to be turned on or off. Magnetic stands allow the indicator to be used on a metal surface, such as on the face of a machine spindle. Select an indicator with enough range to perform the measurement. If you are using a dial indicator, you can determine if the travel is adequate by checking the length of the spindle. The indicator which is selected must be rated at the correct degree of accuracy. Remember to follow the 10-to-1 rule, which you learned about in an earlier lesson. Suppose, for example, that you are measuring a dimension which is stated in thousandths. This indicator cannot be used, since it only measures to the nearest thousandth. To provide repeatability, an indicator which measures in tenths would be needed. Select either a metric or an inch indicator, depending on how the print is dimensioned. While measuring with test indicators, the lever should be positioned as close as possible to 90 degrees from the direction of measurement. If the lever is positioned incorrectly, it can cause measurement errors called cosine errors. Cosine errors result from measuring with the lever at an angle greater or less than 90 degrees. The contact point must have enough pressure to provide a true reading. Be sure that there is from 1/10 to 1/4 of a rotation of the needle before you start measuring. Part 2. Surface plates and holding devices. Open setup inspection is usually done on a surface plate. Surface plates are made of solid granite, which is ground and lapped to an extremely high degree of flatness and smoothness. Different types and grades of granite can be used depending on the quality and durability required. Large surface plates may be permanently mounted to a solid table. This is called an inspection table. Smaller, portable surface plates can be set up on a workbench or a cart. Use caution when working on a surface plate. Although they are hard, they can be scratched or chipped. To prevent scratching or marring the surface, avoid sliding objects or measuring instruments over the top of the surface plate. When placing items on a surface plate, set them down gently. Be sure that all workpieces and measuring instruments used on a surface plate are free of chips, dirt, and oil or coolant. Before a workpiece can be measured in open setup inspection, it may have to be fixtured or placed on a holding device. Workpiece holding devices provide stability during measurement and consistency in the measurements. Sometimes they are used to hold the workpiece at the required angle or height. For dimensions which are measured from datums, the datums may have to be established using workpiece holding devices. Many different holding devices are available. The proper device must be chosen based on the size and shape of the workpiece and on the type of measurement to be done. As you fixture workpieces in open setup inspection, remember to fixture them by the correct surface or feature. Fixturing or holding the workpiece by the wrong feature could result in inaccurate measurements. This is a V-block, a commonly used holding device. V-blocks are easily recognized by the V-shaped cavity where the workpiece is placed. Often, V-blocks can be magnetized to make sure that the part is held securely. The magnetism can be turned on or off using an on-off lever at the end of the V-block. Some V-blocks have clamps available for clamping the item being measured. This is particularly useful for fixturing non-magnetic materials such as titanium. A typical datum used in lathe-type workpieces is the axis of a cylindrical feature. Often, simply placing the datum feature in a V-block and rotating the workpiece establishes the datum. A chuck can sometimes be used to establish the datum axis from a cylindrical feature. For cylindrical workpieces, the datum feature sometimes consists of a pair of center holes. In this case, a center fixture such as this must be used to hold the part for inspection. This feature control frame calls out a runout tolerance. The datum to be used for measurement is shown as datum features X and Y, separated by a dash. This is an example of a coaxial datum. A coaxial datum is the axis formed by two coaxial workpiece features. For common datum features, which are outside diameters rather than center holes, an adjustable V-block such as this may be used. The two blocks are moved up or down the angled tracks on the base until they are the proper distance apart and the correct height. Then an indicator or other measuring device is used to perform the measurement. These matching steel bars are called parallel bars, or simply parallels. Parallel bars can also be made of granite. Parallel bars are manufactured so that opposite sides are parallel to each other to a very high degree of accuracy. They are usually furnished in matched pairs, which provides the greatest consistency in size. Here is one example of using parallel bars for fixturing workpieces. The two sides of datum surface B are separated by a ridge. This ridge prevents the datum surface from being placed directly onto a surface plate. In this case, the part is set on two matched parallel bars. This fixturing would be correct because the datum surfaces are smaller than the parallel bars. This assures that the high points of the datum surfaces are contacting the simulated datums. Part 3. Gauge blocks. These commonly used tools in open setup inspection are called gauge blocks. Gauge blocks are rectangular blocks made of hardened steel. They are precisely manufactured for flatness, parallelism, and size to a very high degree of accuracy. Gauge blocks are used for many purposes in manufacturing. They can be used for checking workpieces, for setting and calibrating measuring equipment, and for tool setting and presetting. A shop-grade set of inch gauge blocks typically comes in a set of 81 blocks. Within each set, there are 4 series of blocks. Each series is a family of sizes. The 4th series, for example, consists of the blocks 1 inch and larger. Often, a single gauge block will not be the required size. Various size blocks must be combined to achieve the required dimension. By putting together blocks in various combinations, thousands of different dimensions can be obtained. When selecting gauge blocks to assemble, it is important to use as few blocks as possible. To show the proper way to select gauge blocks, let's use an example. Suppose that we need to assemble a stack of gauge blocks, which is 3 inches, 635 thousandths, and 7/10. The best way to select gauge blocks of a particular dimension is to work from right to left. In this case, we will start by matching the 7/10. The first block to select is from the 10,000th series. The actual block we will use measures 100 thousandths and 7/10. The next 2 digits of our target dimension, going right to left, are 35 thousandths. This block from the 1000th series measures 135 thousandths. The next series of gauge blocks is the 50,000th series. Blocks from this series should be selected to bring the total measurement to the nearest inch. Remember that the blocks we've already selected have each added 100 thousandths, so to reach the nearest inch we will need to add 400 thousandths. This is the 400 thousandths gauge block. This gauge block is added to the others already selected. The final step is to add the whole numbers from the target dimension. From the 1 inch series of blocks, we select the 3 inch block. Our stack now equals the required dimension. We have used the fewest possible number of blocks to achieve that. Once gauge blocks have been selected, they must be assembled together so that they can be used as a single unit. Assembling gauge blocks is called ringing them. A stack of gauge blocks which have been properly rung will bond into a single unit. To ring gauge blocks, be sure that they are clean. Even the oils from your hands will prevent a good bond between the gauge blocks. To remove these oils, rub the shiny surface of the gauge blocks on a piece of blank white paper. Avoid printed pages because the ink may rub off onto the blocks. Rub in either a circular or a figure 8 pattern. Hold the two largest blocks so they overlap at the edges. Then carefully slide them together, applying a slight pressure. To see if the rung blocks have bonded, pull gently on one block or lift the stack by one block. Finish by ringing the remaining blocks onto the first ones. To help prevent any errors, you should measure the finished stack to double-check the size. When you are done with a stack of gauge blocks, disassemble them by sliding them apart. Remember to clean them before replacing them in the storage case or cabinet. Part 4. Height gauges. Height gauges are commonly used in workpiece measurement, including open setup inspection. Height gauges, as the name implies, measure the height of workpiece features and surfaces. Some height gauges must be used on a surface plate. These height gauges use the surface on which they rest as the origin of their measurements. Other height gauges have a built-in table or other precision surface from which measurements are made. These self-contained height gauges can be used nearly any place, since a surface plate is not required. Major components of a typical mechanical height gauge include the base, which supports and stabilizes the other components, a post attached to the base, which allows up and down movement for measurement, a slide, which slides up and down on the post, and a device which contacts the surface being measured. On this gauge, a test indicator is being used. Other components which can be used to contact the surface being measured include a depth rod attachment, a spindle similar to that found on a dial indicator, or a blade-shaped arm called a scriber. To perform a measurement with a height gauge, there is normally a locking nut or handle which allows the slide to be positioned at the approximate required height. The rough adjustment may have to be locked back down before fine adjustment. After rough positioning, there will be a fine adjustment device such as this knurled nut to touch the scriber blade to the feature being measured. This height gauge has a hand wheel which moves the slide up and down. On standard mechanical height gauges, there are three types of measuring systems. They are vernier scales, dials, and digital readouts. Vernier height gauges have a vernier scale which is used to read the dimension being measured. This scale works like a scale found on a vernier caliper, which you learned to read in an earlier lesson. Dial height gauges have an integrated dial which shows the current measurement. Digital height gauges provide a digital readout of the dimension being measured. Suppose that on this sample workpiece, we need to measure the distance from this shoulder to the top surface. With a vernier height gauge, we would need to measure the heights of both surfaces. Then we would have to subtract the lower dimension from the higher one to determine the measurement. With a digital readout, the calculation is not necessary. To measure the dimension, the spindle is touched off on the shoulder. By simply pushing a button, the readout is set to 0. After touching off on the top surface with the spindle, the measurement is shown directly on the readout with no calculation required. This is a type of height gauge called a Cadillac height gauge. A Cadillac height gauge is not used to measure workpieces directly. Instead, it is used to create precision height settings, which can then be used for comparison to the dimensions being measured. The Cadillac height gauge has 2 rows of alternating precision blocks, similar to gauge blocks. Each block is exactly 1 inch in height. On the top of the gauge are a micrometer head and a mechanical readout. Exercise caution when using a Cadillac height gauge. Do not move it quickly to either end of its range of travel or move it down until it strikes the surface plate. Doing these things could jar the gauge out of calibration. Some surface plates are made with a pocket, such as this one. The pocket provides clearance for moving the gauge column near to the surface of the surface plate without striking it. As an example of how to use the Cadillac height gauge, suppose that we need to measure the height of the top surface of this bored hole. We are measuring from the datum plane on the bottom of the workpiece to the top of the bore. The standard height gauge has a test indicator installed on it. With the bottom of the workpiece, the datum surface, on the surface plate, the indicator is touched off on the top of the bore. The operator zeroes the dial on the indicator. Then the indicator is moved to the Cadillac height gauge. The operator turns the micrometer head on top of the Cadillac height gauge to bring the nearest gauge block to meet the tip of the indicator. The Cadillac height gauge is adjusted until the indicator once again reads 0. If the measurement had been of a surface below the indicator tip, then the indicator would be touched off on the top of the adjacent gauge block. Now the measurement can be determined. The numbers on the front of the Cadillac height gauge show the nearest inch. This measurement, for example, is above the 4-inch line, so the whole inch part of the measurement is 4 inches. The mechanical readout shows measurements to the nearest thousandth. Our measurement, therefore, is 4 inches and 317 thousandths. If we needed a measurement to the nearest 10 thousandths, the dimension could be taken from the micrometer head instead of from the mechanical readout. This is a type of height gauge called a comparator. Comparators are typically used to measure heights and diameters. A surface plate is not required when using a comparator. Comparators are extremely accurate measuring instruments. On this comparator, for example, each increment of the dial is rated at 20 millionths of an inch. Each of the larger numbered marks measures a tenth. This comparator has markers which represent the limits of the tolerance range. To prepare the comparator for measuring workpieces, the limit markers must be set using these tangs on the back of the gauge head. The 0 mark on the gauge should represent the nominal dimension for the part being measured. Set the limit markers so that they are the correct distance above and below the nominal for that part. Next, gauge blocks must be selected and rung together, which equal the upper and lower tolerance limits. With the gauge blocks under the needle, the head or the table can be rough adjusted up or down after loosening the appropriate locking knob. Rough adjust the gauge until the dial is close to the target limit line. Then fine adjust the dial using this fine adjustment knob until the dial is at the correct dimension. To check workpieces, the part is placed on the gauge's table. Then it is swept back and forth under the probe to locate the highest point on the surface. The dial on the gauge shows the variation in the diameter from the nominal. The limit line markers will show whether the part is within tolerance. This is an electronic height gauge. Electronic height gauges provide very accurate measurements and are often easier to use than mechanical height gauges. Many of them have built-in time-saving functions, such as automatic calculation of whole center lines. The basic components of electronic height gauges are similar to those of mechanical height gauges. There is a vertical post, a slide which moves up and down on the post, and a device which contacts the surface being measured. In this case, a probe with a ball on the end is being used for measurement. Other devices can be used, such as a depth rod. This height gauge has a digital display where the measurements are shown. The push buttons on this control panel are used to perform numerous functions, such as to set the 0 point for a measurement and to select either inch or metric dimensions. Many electronic height gauges have additional features which are not possible with mechanical height gauges. An example is this data port. The data port allows automatic output of measurements to a computer or other data-gathering device or to a printer. On this height gauge, an electric motor moves the slide up and down on the post. These two levers control the motor. Pushing in the upper lever will move the slide up. Pushing the lower lever will move the slide down. To remove the probe and install a different one, this set screw is loosened. Then the probe or other device is slid into place and the set screw is tightened. When a contact device such as this probe is used, the diameter of the tip may have to be added to or subtracted from the measurement. Let's look at why. When the tip of the probe contacts a surface, the center line of the probe is offset from the surface. The center line is offset by the radius, which is 1/2 the diameter of the tip. When a measurement is made from one top surface to another top surface, the tip is offset in the same direction. Because the offset is the same for both points of contact, the actual measurement is correct. This same principle applies when touching off on two bottom surfaces. When measuring from a top surface to a bottom surface, however, the probe is offset in opposite directions. This means that the actual measurement is incorrect. Because the tip is offset in both directions, the correction amount is twice the radius, which equals the diameter of the tip. This correction amount must be either added to or subtracted from the measurement. If the measurement offsets the tip toward the other feature, the measurement value will be less than the actual dimension. When this happens, the diameter of the tip must be added to the measured value. If the measurement procedure offsets the tip away from the other feature, the measured value will be greater than the actual dimension. In this case, the diameter of the tip must be subtracted from the measurement. This electronic height gauge will automatically compensate for this probe offset error. The probe tip diameter must be entered after changing to a different probe. This allows the gauge to compensate for the probe offset error. To enter the probe tip diameter, two gauge blocks must be rung together as you see here. The two blocks must be offset from each other to provide surfaces for touching off the gauge. The gauge must, of course, be powered on. This height gauge has an on-off push button on the control panel. Next, this button with the probe symbol on it is pressed. Two flashing arrows appear on the display, indicating that the probe must be touched off in both directions. Then the operator touches off the probe on the surfaces of the gauge blocks, which are contacting each other. Both the lower and the upper contacting surfaces must be touched off. After both surfaces have been touched off, the flashing arrows will be gone. The diameter of the probe tip is now entered into the gauge. Different models and styles of electronic height gauges operate differently with different controls and displays. As an example of how one works, we will look at a simple measurement done with this height gauge. For our example measurement, we will measure the distance from the top of this upper collar to the bottom surface of the lower collar. Before any measurements are done, the surface plate must be cleaned, as well as the workpiece and any fixturing or holding device. The operator then touches off the probe on the first of the two surfaces. With the probe touching the surface, this push button marked Preset is pushed. This sets the 0 point for the measurement and zeros the display. Now the operator simply moves the slide down, then in to touch off on the second surface to measure. At this point, the measurement of the dimension is shown on the digital display. Many other types of measurements can be done with electronic height gauges. Some examples would include measuring to the center line of bored holes, measuring ID heights and distances, even measuring runout. You should check with your leader or instructor, as well as the gauge documentation, for specific procedures. This completes the instruction for Lesson 9, Open Setup Inspection. Ask your instructor for the next step in completing this lesson.